Hello, in this video, I want to continue on machine learning using R, how to use the superSOM function. Okay, so in the R package, kohonen, which is for self-organizing maps, besides the basic function SOM, there's another function superSOM with some advanced features for self-organizing maps. So here's a list of features of superSOM. Unified multi-layer architecture. So it trains a single 2D grid where each node holds representative profiles or codebooks for multiple data layers, such as features and labels. Okay. And weighted supervision uses importance weights to emphasize specific layers, example labels during training, making them more influential in map organizations. Okay. And heterogeneous distance rules allows each layer to use its own distance metric, handling both continuous and categorical data naturally. So very flexible. And also missing data resilience. Positions observation using only available attributes, ignoring missing values while anchoring points based on remaining layers. So you can see superSOM has a lot of flexibility for different data types, different weights, and also heterogeneous distance definitions, and also missing data. Okay, so let's take a look. First, you need to install the library kohonen, and then here let's load it in. Set a random seed, create a data set with 3 groups, layer 1, and then give them names, and then give the labels, and then we can simulate, put everything in the data list. And now we have this training data set. We can define an SOM grid. So here we just pick a 5x5 hexagonal grid. Later on, I will talk about a function to actually find some sort of optimal number of the dimension for the grid. Okay. So the training for the grid is SOM grid. You can use the x dimension equal to 5, y dimension equal to 5, topo equal to hexagonal. Then let's define the grid. Okay. Now we can train the model. We can give the measurement a weight of 1 or class of weight of 2. Okay. So corrected call using user.weights. Okay. So you can use superSOM. So put in the data and the grid equal to SOM grid, and then use the user weight C12 and keep the data equal to true. And then once you fit it, you can print it out. It'll give you some basic information about this self-organizing map. Okay. So then we can extract a lot of information about this SOM. First, let's visualize the results. This plot is called the training progress. It's the mean distance to the closed unit. It should go down. You have 2 lines here. One is for continuous data measurement. The other is for the categorical data for classes. Okay, so they're all going down and become really small, around 0.002. Okay. Second is we can do another plot for the codes, the weights of the variable in each node, and to see numerical variable weights. Okay, so here, I'm sorry. I think I need to show this one first. So this one is the layer 1 for the measurement. You can see there's a 5 variables. You can see these kind of like at each node, you can see the distributions of these 5 variables. Some nodes with a lot of the variables, some with only a few. Okay. So it's quite heterogeneous in this map. The second layer is the class one. So you can see type A, type B, and type C, how they distributed across different nodes. Okay. And then you can do plot 3, which is the mapping the original class. You can see the cluster maps. You can see for each node what kind of clusters are in there. Okay. And once you have a fitted self-organizing map, you can also do prediction with new data. So we can create a new observation, get its column names, and create a list as new data. Then we can use the predict function, just put in the fitted model and just new data equal the new data list. And create the prediction, and then we can print it out. It gave us its mapped to type B there. Okay. All right. And we can evaluate the quality of the maps. Okay. So one measure is the quantification error, just the mean of all the distances. In this case, it's 0.0022. Okay. And we can do plot the quality distance of each point to its node. So you can see this is the quantification error per node. Here you can see the darker the color, the smaller the errors. So what you want to see is relatively even low nodes across the map. So we have a large number of low error nodes, but also some like white or gray. So, and it's not very even. So the quality of our map is not very good. And the second map we can do is the neighborhood map of distance for the U matrix. And for this one, you also want to look at the good mix of light, which corresponds to valley, and dark color, which corresponds to edge of a wall here, which is the case here. And then one smooth color progression, which is, yeah, I think relatively okay, because similar color really are next to each other. Okay, with few rare exceptions here. All right, and you can plot out layer specific quality for this one. This is the observation per node. This is, I think, for the continuous one. And also similarly, you want even spread of colors. So this is okay, but not very, very high quality. Okay. And then we can extract the cluster assignment, because this is a cluster analysis. You can use SOM as a cluster analysis. You need to know the eventually the cluster for which observation you classify which node. So this is the first 6 rows of this result matrix. You can print out this matrix. This is just 60 rows. You can see how these original labels are kind of classified into different nodes. And the grid X, grid Y, there's a coordinates in the that hexagonal grid. Okay. All right. We can also group nodes into superclusters because we have hierarchical clustering. We can on the code book vectors because there's too many clusters. Sometimes we want to kind of collapse some clustering into superclusters. And you can use the cutree function and cut into 3 clusters, and now you can see it look like that. There's 3 colors. Okay. You can also export your data, the results, into a CSV file in case you want to run analysis on the CS file using other programs. So I'm not going to run that. And here is a function choose grid size, which is sort of like number of factors in factor analysis, or number of principal components in the principal component analysis. It's like not exact science, but art. So here there is a rule of thumb developed by Vassano and et al. Usually, optimal number of a grid size would be 5 times square root of n, where n is the sample size. So here I just present this grid function, an example of running the grid. So here it recommended 7 by 7 for 60 samples. And if you have a large data set, for example, you have 2,000 samples, it recommends a 15 by 15 grid. Okay, so I'm not going to spend more time on this. I just demonstrate the use. One big strength of superSOM is it handles missing data. So here is some code to generate a data set with some missing values, and then so you can see we got 30 missing values in here. Then we can use the superSOM function to train the model. You can see the syntax is exactly the same, so you don't have to do any special treatment. It just automatically handles missing data, and it does not do list-wise deletion like many other R packages. So it has the internal process of distance scaling and then best matching. But there's a limit on how much missing data you can tolerate, controlled by an argument of max ENA dot fraction. You can read the help documentation to figure out that. And then you can check the convergence, and you can use it to do the imputation, and then you can print out the imputed values. Okay. So this is the introduction of the superSOM, which is a very powerful, very flexible tool for performing self-organizing maps. And it's really worth mentioning. I hope you learned something here. And again, I'll share our codes in the comments area so that you can use it for practice, modification, and probably use for your own data set. Thanks for watching.